They said the mountains were stable. They said the snowpack was secure. They said the storm would pass. Above the French Alps, it didn't. It stalled over the peaks like a weight that refused to lift. Pressure thickened, snow layered, silence deepened. Instruments began to flicker as satellites watched the system tighten instead of fade. What looked harmless from a distance was quietly gathering force. The sky held its breath. The ridgelines carried more than winter. They carried strain. Deep inside the slopes, unseen fractures stretched through buried layers, delicate as glass, tense as wire. Nothing moved. Then everything did. A single break whispered across the mountain. A sharp report swallowed by distance. The surface shifted. The slope released. Gravity answered. What began as a line became a surge, and what became a surge became motion. No human command could stop. This was not a storm passing. This was a storm settling in. This is Storm Nils, and this is the moment the mountains decided they would no longer hold. 3 days before the first avalanche, the Alps looked almost peaceful. The sky hung low and pale over the ridgelines. Villages moved through their routines. Ski lifts turned. Roads remained open. There were no towering storm walls, no violent lightning tearing through the clouds, no dramatic warnings scrolling across television screens, just snow. But it wasn't ordinary snow, it fell steadily, hour after hour, in thick, moisture-rich bands drifting in from the south. Not the light, powdery flakes that scatter in the wind. This snow carried weight. It landed softly, then compressed under its own mass. By morning, rooftops sagged slightly deeper. By evening, tree branches bowed lower. Meteorologists in southern France began to notice something subtle in their data streams. The snowfall wasn't fluctuating the way most winter systems do. There were no clear pulses, no breaks between fronts. Instead, the accumulation graph climbed in a near-perfect upward curve. It was stacking, layer upon layer, uniform, dense, moist. At regional forecasting centers, radar screens glowed in quiet rooms as pressure maps revealed a rare alignment. A stubborn, high-pressure block over Central Europe refused to shift. To the south, a low-pressure spiral pulled moisture north from the Mediterranean with mechanical consistency. Between these two systems sat France, caught in a corridor of continuous feed. Storm systems are supposed to migrate. They pass through, deposit snow, and move on. This one lingered, and that changed everything. Snowfall totals quietly exceeded projections, 20 centimetres, 40, then 80 in exposed alpine zones. On paper, those numbers were significant but not unprecedented. The Alps are built for winter. But the real concern wasn't depth, it was structure. Inside the growing snowpack, distinct layers began forming, each storm cycle pressing down on the one beneath it. Warmer intervals created thin crusts. Colder returns laid fragile crystals on top of what observed those crusts. The bonds between layers weakened. To the untrained eye, it was just white terrain stretching to the horizon. To an avalanche forecaster, it looked like stacked glass, separated by powder. Scientists call them persistent weak layers, buried instabilities that can remain dormant for days or even weeks. They don't announce themselves, they wait. They allow the surface to appear calm while tension builds below. And as Storm Nils continued to feed moisture into the mountains, those hidden fault lines multiplied, quietly turning stability into uncertainty. Storm Nils did not explode into existence. It did not announce itself with dramatic satellite spirals or record-breaking gusts. It evolved quietly, methodically, within a larger atmospheric pattern that had been building for days. Over the Mediterranean, surface waters remained slightly warmer than seasonal averages, feeding moisture into the lower atmosphere. At the same time, a surge of Arctic air descended from Scandinavia, dense and dry, sliding southward with precision. When that cold air collided with the moisture plume over southeastern France, the contrast created lift. Lift created clouds. And clouds began to thicken into something organized. Cold met wet. And instead of moving east, the system slowed. A blocking high-pressure ridge over Central Europe acted like a wall. Storm Nils pressed against it and stalled, trapped in a corridor that funneled moisture directly into the French Alps. On satellite imagery, the structure didn't look violent. It looked steady, almost symmetrical. But beneath that calm geometry, the core was strengthening. Meteorologists monitored the central pressure as it gradually dropped, not dramatically, but consistently. Wind bands tightened around the low. Precipitation rates intensified, not in explosive bursts, but in sustained sheets of snowfall that refused to taper off. What made Nils different wasn't aggression. It was endurance. Instead of delivering sharp gusts capable of scouring slopes clean, it laid down snow with persistence. Hour after hour, flakes accumulated, compacted, and bonded unevenly. Without strong winds to immediately redistribute it, much of the mass settled directly where it fell, adding uniform load across wide sections of terrain. 72 hours passed with minimal sunlight breaking through the cloud cover. Surface temperatures hovered near freezing, warm enough to keep the snow slightly moist, cold enough to preserve fragile crystal structures within the deeper layers. That combination produced density at the surface and weakness below. The snowpack grew heavy, compressible, increasingly unstable. Then came a subtle shift. Wind direction veered just enough to begin transporting snow laterally across slopes. Cross-loading intensified along ridge lines. Natural bowls collected deeper drifts. Cornices formed along exposed crests, overhanging shelves of compacted snow extending into open air. From a distance, the mountain still appeared serene. But the terrain was being reshaped by invisible forces. Load was concentrating in specific zones. Stress was redistributing unevenly. And each newly formed cornice, each drifted pocket, each wind-loaded ridge became a potential trigger point. The storm had matured. The mountains were absorbing its weight, and no one yet knew how many weak points had been quietly created. Morning arrived with deceptive calm. Church bells echoed faintly through an alpine village. Smoke rose gently from chimneys. The sky had cleared just enough to reveal fresh white slopes glowing under the pale light. It looked pristine, balanced, almost harmless. Then the mountain answered. The first avalanche came without warning. It didn't begin at the summit, where winds had carved dramatic cornices. It didn't start on the steepest, most intimidating face. It released from a mid-elevation slope, long categorized as relatively stable. A slope that had held through countless winters. A fracture line shot across the surface like a zipper tearing open fabric. A crack, then movement, then acceleration. The slab detached cleanly, gliding forward before gravity seized control. Snow surged downslope in a dense, cohesive mass. It didn't explode into powder. It flowed like concrete in motion, thick, forceful, unstoppable once momentum took hold. The rumble followed seconds later, a deep rolling sound that vibrated through the valley floor. Within hours, a second slide was reported several kilometers away. Different aspect, different elevation, similar structure. Then a third, each triggered independently yet connected by the same buried weakness running through the regional snowpack. The emergency channels filled with measured but urgent communication. Authorities elevated warnings, ski resorts halted operations. Mountain roads closed as a precaution. Patrol teams scanned known avalanche corridors. But something unusual was unfolding. These were not isolated releases responding to a single trigger. They were cascading events. Each avalanche stripped weight from one section of terrain while transferring stress to another. Slopes that had appeared marginally stable in the morning were compromised by afternoon. Drone surveys revealed multiple fresh crowns etched across mountainsides, long, clean fracture lines marking where slabs had broken free. Entire faces were recontoured in hours. Support structures within the snowpack were collapsing sequentially. It was a chain reaction without a single origin point. By nightfall, avalanche activity had been documented across several alpine departments. Forecast centers escalated danger ratings to level 4, high risk, then issued localized level 5 alerts, the highest classification reserved for widespread natural releases. Yet, what unsettled experts most was not the intensity, it was the persistence. Snowfall had begun to taper, skies were stabilizing, winds were moderating, and still the mountains continued to release. Because the threat was no longer falling snow, it was the immense weight already resting on fragile layers beneath the surface, pressure that had not yet finished redistributing itself. Avalanches are not random acts of nature. They are the visible outcome of invisible mechanics, precise, measurable, governed by physics. Gravity pulls downward. Friction resists motion. Bond strength holds layers together. When those forces fall out of balance, the mountain adjusts. Storm Nils had constructed a snowpack with complexity hidden beneath its smooth white surface. Layer after layer had settled over days, dense slabs resting atop weaker crystalline grains, formed during brief temperature shifts. Imagine stacked panes of glass, separated by fine powder, stable at first glance, fragile at the seams. When the load on the upper slab exceeds the cohesion of the layer beneath it, failure begins, not gradually, but suddenly. A fracture initiates at a weak point, sometimes from a natural stress concentration, sometimes from subtle settlement within the snowpack. That fracture then propagates outward, and propagation travels fast. Under the right conditions, cracks can race across a slope at speeds exceeding 100 kilometers per hour, faster than a skier could escape, faster than the eye can fully register. The entire slab can detach within seconds once the bond fails. Slope angle plays a decisive role. Most slab avalanches occur between 30 and 45 degrees, steep enough for gravity to overcome friction, but not so steep that snow constantly sloughs off before building depth. Much of the French Alps sits precisely within that critical range. But Storm Nils introduced additional stressors. Atmospheric pressure fluctuations during the storm's slow exit created subtle changes in compressive force on the snowpack. Rapid micro-drops in pressure slightly reduce the external weight pressing down on the surface. The effect is small, but in a system already near failure, small changes matter. Instruments can detect it. Snow responds to it. Then there is terrain amplification. Alpine valleys funnel wind with precision. During Nils, shifting air currents redistributed snow unevenly, depositing heavier loads on leeward slopes and convex rolls. Natural bulges where stress concentrates. Balls collected drifted snow beyond seasonal averages. Cornices extended farther than they appeared from below. The result was localized overload, even after snowfall ended. Because avalanches are not triggered solely by new snow, they are triggered when internal balance collapses. Storm Nils built the imbalance carefully, layer by layer. When the skies cleared, the energy remained stored within the structure. The storm had moved on, but the instability it engineered was still settling, still adjusting, still searching for equilibrium. And until that balance returned, the mountains continued to answer gravity's call. Today, the slopes are quieter, but they are not silent. Inside monitoring stations scattered across the alpine region, scientists watch the mountains with patient attention. Screens glow with live data streams. Graphs trace subtle movements invisible to the human eye. Remote sensors anchored deep in the snowpack measure settlement rates hour by hour, calculating how quickly layers compress and whether internal bonds are strengthening or weakening. Acoustic instruments listen as well. Not for avalanches, but for precursors, faint internal fractures, delicate collapses between buried layers. The soft signals of stress redistributing beneath the surface. These sounds are too low for human ears, yet they tell a precise story about structural stability. Above it all, satellite radar passes silently overhead, mapping terrain deformation down to millimeters. A slope doesn't need to slide to reveal instability. Sometimes it only shifts slightly, adjusting its weight, releasing tension in increments too small to see yet large enough to measure. Each reading helps experts understand whether the snowpack is settling safely or approaching another threshold. Scientists are not waiting for the next storm. They're watching what the last one left behind, because instability doesn't vanish when snowfall stops. Weak layers buried deep in the pack can persist for weeks, sometimes longer, insulated from sunlight and shielded from wind. Until those layers bond or collapse, the risk remains quietly present. Researchers are also studying a broader atmospheric trend. Warmer Mediterranean waters can inject greater moisture into winter systems moving toward the Alps. More moisture means heavier snowfall events when cold air arrives. Heavier snowfall means greater loading on mountain slopes. The pattern does not guarantee danger every season, but it increases the likelihood of sharper extremes when conditions align. At sunset, the peaks glow gold and rose, calm and motionless against the darkening sky. To most observers, the landscape looks perfectly still, but experts understand something the casual eye cannot see. In winter mountains, stillness is not always stability. Storm Nils never announced itself with violence. It didn't arrive with thunder or spectacle. It moved quietly across the sky, layering the mountains with patient precision. Hour by hour, flake by flake, it added weight to slopes that had carried winters for centuries. No single moment seemed extraordinary. No single gust signaled danger. Yet all the while, pressure was building. Deep within the snow, deep within the ridgelines, deep within the balance between gravity and resistance. When the mountains finally responded, they did not do so dramatically. They answered in their own language, on their own schedule, through motion shaped by physics, older than memory. The storm had already weakened by then. The clouds had begun to thin, but what it left behind continued its work long after the sky had cleared. Haitule. Above the valleys, the wind faded until only stillness remained. But in the Alps, stillness is never truly empty. It carries tension. It carries history. It carries the quiet decisions of mass and gravity negotiating across frozen slopes. Because the most powerful storms are not always the loudest ones. Sometimes they are the ones that settle in silence and leave the mountains remembering long after the sky forgets.